Okay, 4.5, basis and dimension. Your homework is there. It seems like a lot, 1 through 69, but it's every other odd, so it's not that, ooh, make me dizzy. It's not really that much. Okay, so we have this set of vectors again, same thing, in a vector space V. We say that this set of vectors is a basis for V if it spans V. In other words, um, every single vector in V can be formed by a linear combination of these vectors, but this vector set is linearly independent. In other words, none of these vectors can be written as a linear combination of the others, but every vector in the big space V can be produced using these. We say that that's a basis. What it is, a basis, is a spanning set that is just the right size, okay? It's got enough vectors to span V, but it doesn't have so many vectors. It doesn't have anything it doesn't need. It doesn't have any extra vectors, because if it has any extra vectors that are not necessary, then one of them will be a linear combination of another, okay? So you take a spanning set and you check to see if it's linearly independent. If it is, then it is a basis for that vector space V. All right? Now, the book talks about a standard basis, but it never really tells you what it is. Okay, but the standard basis is just the simplest, most recognizable, easiest to find basis for any set. Some examples of standard bases for three-dimensional space, all of the points x, y, z. Your standard basis is going to be a 1 in the x space with zeros, a 1 in the y space with zeros, and a 1 in the z space. Do you see what I mean by being the easiest to find and the most recognizable? Um, the vector space of all second-degree polynomials. So that's x squareds, x's, and constants. Notice that R3 has 3 vectors in its basis, but P2 you would think would have 2, but it has 3 because we have a second power, a first power, and the constant. And I talk about that a little bit more later too. All right, theorem 4.9, uniqueness. Don't let this confuse you, okay? If S is a basis for this vector space, then every vector can be in V, can be written as a single unique linear combination of the spanning set vectors, okay? So each vector in V can only be written one way. However, recognize that each vector in V is a unique linear combination of vectors in the basis, but the basis itself is not unique. A vector space may have many, many, many different bases. That's why we talk about the standard basis. So just because it doesn't look like a standard basis doesn't mean it isn't a basis. You can find many different bases for a vector space, and the bases in themselves are not unique. Okay, so theorem 4.10, same set of vectors here. If that is a basis for V, then every set containing more than n vectors, notice that there's n vectors here. If you get another set that spans V, but it has more than n, it is not linearly independent, because you will have to, if this set spans V, if it's a basis, then you get an extra vector in here, you're pulling another vector out of V and putting it in this set, then you know that you're losing your linear independence because this set is a basis. Makes sense? Every vector in V can be written as a linear combination of these n vectors. So if I have greater than n vectors in there, it's not linearly independent anymore, and it's no longer a basis, it's just a spanning set. All right, we're going to talk more later about the number of vectors in a basis, but Theorem 411 says that if a basis of V has n vectors in it, then every single basis of that space will have that many vectors. Okay, it's very important that you know that. For it to be a basis, it has to have a certain number of vectors, no more and no less. For an example, an nth degree polynomial will have n plus 1 vectors in it. Remember, you also have to have the constants, not just the n powers of x. Our real space, n-dimensional space, has n vectors. The number of vectors in a basis of a vector space is called the dimension, and that's what we were talking about. If the vector space has n vectors, then every basis is going to have n vectors, and n is called the dimension of V. So what you have to do is take your spanning set, check to see if it's linearly independent, then you know you have a basis. And however many vectors are in that basis, that's the dimension of your space. The dimension of, say, m by n matrices is going to be m times n. You'll see that a lot. If your matrix is square, n by n, then you've got n times n as your dimension. Now, I want to point something out so you don't get confused with some of the example problems. A triangular matrix, m squared, let's say, and it's triangular. In other words, it's in row echelon form. You have zeros either above or below the diagonal. That is just a subset of the m by n matrices. If you have a symmetric matrix, in other words, you could flip it on its diagonal and get the same exact matrix. That is also just a subspace of the n by n matrices. So when you're checking for the dimension of either a triangular or a symmetric, you may have fewer than n or n squared vectors in it. You may have a lower dimension, and I spelled dimension wrong. I don't know how to spell it. There we go. Dimension. Because it's just a subspace of the regular space, it may have a different dimension. Okay. Next, the dimension of the subspace is always less than or equal to the dimension of the entire vector space. I think I said that more than once, but you get it. Okay, in a case where you know the dimension of your vector space, as in, for instance, R3, three-dimensional space, you know the dimension is 3, right? Didn't I mention three-dimensional space? Three-dimensional, right? Okay, so if you know the dimension of the vector space, then there's no need to check for both linear independence and span. You know you don't have too many or too few vectors. You will have 3 vectors for three-dimensional space. All you have to do is check for one of those conditions. Does it span, or is it linearly independent? If one of those is true, then both of them will be true. If one of them is false, then they will both be false. For example, any set of 3 linearly independent vectors, but this is a big statement, by the way. Any set of 3 linearly independent vectors in R3 will span R3 and is therefore a basis because it spans R3 and they're linearly independent. And that comes just from knowing that there are 3 vectors in the basis of three-dimensional space. And while I'm here, let's write this correctly. There we go. Did it again. Whoops. There we go. All right, get on it.